Okay, we're now being recorded for the YouTubes. Oh, hang on, something's being. Jack can talk about that.
Yeah. So yes, the homework due date is being pushed to Monday because we haven't finished with the tunneling stuff. And I thought about the final. Um, so I was thinking maybe sending that out by May 1st, and then that gives you several days to work on it, and then it could be due at 5 p.m. on May 5th, which is when the final is supposed to end. Um, and so then it'll be a take home. And then I was also looking at the percentages, you know, what the syllabus says, and I was thinking of, since there won't be an exam 2, making exam 1 30% of the grade of your course grade, and then the final 45%. And so that just distributes the credit that exam 2 would have been sort of roughly evenly between exam 1 and the final. And then the final, since all the quizzes and the first exam were all on special relativity, um, that the final would be everything after special relativity. The stuff that I covered in class and that Walter has covered online since. Does that make sense? That's right. Nothing for special relativity on the final. Well, I mean, you don't have to worry about it, but it still exists.
I'm glad, because that makes my GPS work, right?
Exactly. All right. So that's uh, basically what I've come up with. Um, so I don't know, Walter. Do you want to take it from there?
Sure,
Tunneling.
sure, I can do that.
Get as far as we get.
Yeah, I mean, I think we'll get through tunneling today. Um, so let's review what we had done um, last time. So last time we saw that. Let me just push a few buttons here. Yep. Um, we saw that what we know is that in regions where the potential is constant, there are kind of two forms that the wave function can have, right? It can either be um, oscillatory, which is ae to the um, ikx, so that's an oscillating thing because it's a complex exponential, or it can be an exponentially growing or decaying thing, which is that form. And we saw that if I have any sort of potential, any problem where the potential is something that is piecewise constant, then I can sew together various wave functions of that form um, and sew them together by these boundary conditions, right? To say, all right, let me write down the wave function in one region or the other, and then see that the wave function has to have both its value and its first derivative continuous at the border between those regions. And then we said, okay, let's imagine a potential like this, where um, the wave function is coming in from the left, where the potential is zero, particles coming in from the left, and then it encounters a barrier where the energy of that particle is higher than the barrier, and the barrier goes on forever. And then we said, all right, we kind of expect the solution to look like this, where part of the wave is reflected, part of the wave is transmitted, but since the energy of the particle was greater than the energy of the barrier, um, it's going to be oscillatory in both regions. Um, then we said, all right, let's do the math. We crunched through this, and then thanks to Jack fixing my minus sign, we figured out the amplitudes of the transmitted wave, which was C, and the amplitude of the reflected wave, which was B, in terms of the amplitude of the incident wave, which was A. And then we said, okay, more interesting than the amplitude of the wave is the fraction of the particles that bounce off. And we had to think a little bit and realize that the flux of particles, the rate of particles per time, is equal to the amplitude squared times the velocity of the particles in that region, where the velocity is h bar k over m. So then we put all of that in, we calculated transmission and reflection probabilities, and we found formulas for them. So there's the transmission probability, and here is the reflection probability. So I'm just highlighting the big takeaway points from last time. There are big conclusions, but the important thing is this procedure of sewing together wave functions in different regions. Um, hey Jack, next Tuesday you want to do the WKB approximation and generalize this?
Probably not.
Yeah. There is a way to apply this to potentials that change, but only slowly, that I think is super elegant. But then we said, okay, now let's think about the case where the potential barrier is actually more than the energy of the particle. I didn't really draw a picture of this, but so here this is a case where here's our coordinate axes, right? So something like this. And our potential is 0 on the left, and then some large value on the right. So if a particle comes in with less energy than that, suppose a particle comes in with this energy, I should label my axes here. So that is the potential. This is position, and suppose this is the energy of the particle. Then what we can expect for the wave function, right, is that it will be oscillatory on the left, but on the right, it will decay away exponentially. Oh, come on. Well, here I've drawn only the real part of the wave function since I can't draw complex functions. So on the left, this oscillates. On the right, it decays, and this is the classically forbidden region. Um, since in the classically forbidden region, you could look at it as the kinetic energy being negative or the total energy being less than the potential. So we did some math. We realized that what we needed to sew together were a wiggling thing on the left and an exponentially decaying thing on the right, which is this. So we did that, and we calculated these coefficients. We calculated the so just to remind everybody what these things are, since here's our wave function, A amplitude of incident wave. B is the amplitude of the reflected wave, and d here is the amplitude of the transmitted wave. And then we got to asking, okay, what is b? Now, we solved for it here, and that's where we ended class last time. Vaishnavi asks, is it possible for A to be greater than B? Well, we saw that in the previous case. So in the previous case, where the energy is greater than the energy of the barrier, we saw that B was k minus k prime over k plus k prime times A. And that fraction is less than 1. So yeah, in this case, the reflected wave is less than the transmitted wave. Or excuse me, the reflected wave is less than the incident wave. And that kind of makes sense, right? If you think about like shining light on an interface between air and glass, some of the light will go through, some of the light will bounce off. Um, but regardless, the light that bounces back has got to be darker than the light that goes in. So A is always greater than B. Incident light is always brighter than reflected light. Does that answer your question, Vaishnavi? All right. In this case, though, thinking about greater than and less than gets funny when we have complex numbers. So I did the algebra in a particular way here. It's correct, but it hasn't led us to a conclusion that's like the most obvious. I want to solve these equations in a bit of a different way. Um, I'm going to do the algebra in kind of a different path here. So I know that D is A plus B. So what I'd like to do is I'd like to multiply both equations by kappa. So, so this is where we pick up from last time. So this gives us kappa A kappa A plus kappa B equals kappa D. And then the second equation gives me just what it is. I'll factor out the ik. So ik um, something. That's right. We know that we can, at x equals 0, remember we're applying this boundary at x equals 0. So let me write this. A e to the ikx minus b e to the minus ikx equals minus kappa d e to the minus kappa x. But x equals 0 is where the boundary is. So that means the second equation, I can just get rid of all of the exponentials, right? Because e to the 0 is always 1. So that means that the second equation becomes then instead um, ik a minus b equals minus kappa d. And now I can add those two equations together. We'll take 1 and 2, and then 1 plus 2 gives me um, kappa A plus kappa B minus IKA plus IKB equals 0. So now we can solve for B. And we get that B is, let's see, so it's going to be kappa minus IK over kappa plus IK times A. So we figured out now the reflection equation. Yeah, sorry, I misspoke. I did the right thing, but I said the wrong thing. I multiplied only equation 1 by kappa. Thank you, Eva. Yeah, I just wrote the wrong thing and I said the wrong thing, but I did the right thing. Isn't it kappa A plus kappa B plus IKA minus? Um, oh yeah, you're right. That was an addition. Thank you. My problem is like I don't really get a chance to prepare for this class because I'm teaching the other ones, and yesterday was kind of nuts. So I apologize for mucking up my algebra here. Yeah, you're right. We added 1 and 2, so those signs are that way, and that means that this is a plus sign in the numerator, and that this in the denominator is a minus sign, kappa minus ik. Um, and yes, that is the right result. I have a few notes next to me, and I do have the result there. Um, so I want to talk about what this means. So Vaishnavi asked something really penetrating earlier, said, is this greater than A? We'll flip it around. So let's ask, so is this value for B greater than, less than, or the same as A? So we're asking about the reflected wave. So you tell me, is that value for B greater than or less than A? What does that even mean? What does it even mean to talk about greater than or less than for complex numbers? Does anybody have an idea? Mm. Ah, so let's think about how we envision complex numbers. Um, remember that on complex numbers we can graph them on a plane tool where we think of the horizontal axis being the real part and the vertical part being the imaginary part. So if I have, say, um, some value, right? Like let's just make up a number. So let's say that x equals a plus bi. Then the way we would graph x would be to say that x is this arrow, and this part here along the real axis would be the real part, and this part here along the imaginary axis would be the imaginary part. So if you're comparing kappa plus ik to kappa minus ik, so now let's see how this applies to the complex plane. So let me draw another set of axes here. Tools. One second. Here we are. So here's another set of coordinate axes. So again, there's here's the imaginary axis, here's the real axis. And yeah, so k is positive, but ik is an imaginary number. Like you can't adding an imaginary number to an ordinary number doesn't make it either greater or less, it makes it different. So it's not like plus ik makes it bigger and minus ik makes it smaller. They push it in different directions on the imaginary plane. So if I think of, let's say, this vector boop, going out here as kappa plus ik, and this vector here, then kappa minus ik would be that vector. So one of these vectors is not like bigger than the other. They just point in different directions. Does that make sense, Yanju? Okay, so we've kind of been tap dancing around when we say bigger or smaller. So how do we assess which one of these is bigger? What does it even mean for a complex number to be bigger than another one? Does anybody have any suggestions? Magnitudes, yeah, because the magnitudes tell me, that's what James wrote in symbols. Yeah, so really what we should be doing, we want to compare the magnitudes of A and B. And what we've just learned, right, is that they're going to be equal. They're equal since, so we saw that kappa plus ik and kappa minus ik have the same magnitude. So um, uh, kappa plus ik over kappa minus ik has a magnitude of 1. Um, so let's do out a little bit of math here. I just want to show you a bit of algebra. This is a pattern that you should recognize. So what we got, as a reminder, was that B equals kappa plus ik over kappa minus ik times A. But let's look at its magnitude. What is the magnitude of B squared? This is equal to B um, complex conjugate times B so let's write that out. That's kappa. Well, we'll do the complex conjugate first. So that means to flip I and minus I, right? So that gives us kappa minus ik over kappa plus ik times A star times just B again, kappa plus ik over kappa minus ik times A. So now let's do all of that out. So A star A is the magnitude of A squared. That one's pretty easy. We'll leave that to the side. And then we have to multiply out all of these fractions. So this is going to give us kappa squared plus ik kappa minus ik kappa and then minus I squared k squared. We'll simplify this in a minute. And then I get the same thing in the denominator. Kappa squared plus ik kappa minus ik kappa minus I squared k squared. And then times the norm of A squared. Now, these things cancel, and I squared is just minus 1, canceling the minus sign in front of that. So what this tells us is that B squared, well, the norm of B squared, so the magnitude of the reflected wave is kappa squared plus k squared over kappa squared plus k squared times the magnitude of the incident wave. So this is just 1. And this tells us that the reflected wave has the same magnitude. So how does what come from, Yanju? Ah, you fixed it. So this is kind of what you expect, right? That if I shoot particles at a barrier, the new thing in quantum mechanics, right, is that some of the wave function will penetrate into the classically forbidden region. But the amplitude of what reflects back is the same. But what I'd like to do now is I'd like to set up a more complex problem where the barrier is not infinite. we'll go down here. We'll get a completely new page for this. So do you all remember when we talked about total internal reflection? I think that may have been the first day that I was teaching. Anybody remember that? Yeah, so this is a metaphor for total internal reflection, or rather, total internal reflection is a metaphor for this. So we saw that in a, well, actually, we'll write it down here. Um, so compare to total internal reflection. So our scenario was so we're imagining glass and air, and these pieces of glass and air are very large. They kind of go on forever in some sense. So if this is glass and this is air, you saw that if the angle is shallow enough, the angle of the incident ray is shallow enough, the angle is kind of like the Ava, I'll get to that in a minute. Um, uh, so the comparison, sorry, derailed my train of thought there. The comparison is that the angle is somewhat like the energy. So if the incident angle is small enough, then 100% of the light is reflected. And over here, you have, and I don't know how to draw this, you have what's called an evanescent wave, where the electric field decays exponentially. Um, Eva asked about the signs of the amplitude. How does this scenario compare to the traditional wave behavior? So what we see, so Eva, if I use the term phase shift, do you know what that means? Yeah, good. So what happens at so let's talk about phase shifts in context of um, this reflection. So we saw that B equals A multiplied by, well, I'll just write the thing out, kappa, what was it? Was it plus in the numerator? I forget. Yes, kappa plus ik over kappa minus ik. Yanju, the angle to the boundary. Um, and we saw that this is a thing with magnitude 1. So whenever you multiply a complex number by something with a magnitude 1, it's equivalent to shifting its phase, but not actually changing its magnitude. So you're asking about plus and minus, right? You said same sign, constructive interference, flipped sign, destructive interference. Um, it turns out that, one way to think of complex numbers is they are numbers that can have not just either plus or minus signs, but a continuously variable sign that goes from 0 to 360 degrees. So total internal reflection here doesn't flip the sign in that it changes it from plus to minus. It doesn't shift the phase by 180 degrees. It shifts the phase by some other number of degrees. Because Another way you could write this is you could say that b equals a times e to the I theta, where this is a phase rotation by an angle theta. Um, this idea of thinking of complex numbers as really ways to like encode vectors in a magnitude and angle form is super common in quantum mechanics. So people will often talk about the phase of something. And what they mean is the piece of that that is purely something with magnitude 1. Ava, does that answer your question a little bit? We will see in our next example that come back with a vengeance. So when we talked about total internal reflection before, we saw that it's possible to have an air gap that's only got a finite size. So if I imagine an air gap, whoop, wrong tool. If I imagine an air gap, wrong tool again, I am so sorry. Someday I'll learn to use a computer. So if I imagine an air gap that's only got some finite size, and then I put more glass on the other side, then that evanescent wave will make it to the other piece of glass and can actually turn back into a wave with a real wave number. This is dramatic and remarkable, right? We get a wave with a reduced amplitude, but real. So here we have a real wave, okay, real, and this oscillates. Here in the air gap, sorry, in the air gap we have an evanescent wave. So we've got an imaginary wave number, meaning the thing exponentially decays. But if before it exponentially decays too far, if we put another piece of glass in, we have a real wave again. Um, and this is kind of funny, right? Like you think you have total internal reflection, you think none of the wave penetrates into the air, but it really does. It's just exponentially decaying. And if I put another piece of glass over there, then I have a real wave that comes out the other side. Now you might say, well, wait a minute. Is there something wrong with this picture? I'll ask you this. Some percent transmitted. Is there anything wrong with this? It's going to be deflected. So Danielle, it actually won't be deflected. It would be if it were penetrating into a different kind of glass, but if this glass has the same index of refraction, so if you might imagine, like, they're not quite, I mean, it doesn't really matter because these are like plane waves, um, but they do go in the same direction because if you imagine like air to glass to air, the direction of propagation in the two air segments is the same direction, Danielle. Um, but if you imagine glass to air to glass, it works the same way, even though inside the air you have like you're going in an imaginary direction. Nick has it. How can you reflect 100% and still transmit more? Well, what happens is that the evanescent wave reflects off of the glass surface on the other side. This I just simply cannot draw, so I'm sorry, but I don't know how to draw imaginary arrows. But the evanescent wave goes through. Some of the evanescent wave bounces back and then becomes real again and interferes destructively and gives me less than 100%. And it all winds up conserving energy perfectly. So what I'd like to do now, so do you all understand like how this goes with air and glass and light and so on?
Sorry, could you just repeat that last little bit about the evanescent wave? My brother was asking me a question.
Sure, of course I can. So what happens, and say hi to your brother for me. Um, what happens is let me draw, you know, drawing arrows here and wiggles is hard. So let me just draw these big blocks. So glass, an air gap, and then glass again. And here I'm just going to draw straight lines. So this is the incident real wave. And that gets reflected. No, actually I do need to draw them slightly sloped. So that has total internal reflection. So it comes back, and the purple arrow has the same magnitude as the red arrow. Right, that's the thing we just figured out. But the evanescent wave penetrates into the glass, right? So what you get is this evanescent wave continues this way and will then turn back into a real wave once it hits the other glass. With me so far?
Yep.
So green is going to be evanescent and red or purple is going to be, well, green or blue is evanescent. But the evanescent wave actually partially reflects from that boundary, right? It's allowed to do that. I mean, real light can reflect, so like imaginary light can reflect too. And then that means that that is going to turn back into another real wave. So I've got actually two reflected real waves now. One of them reflected off the front of the air gap, and the other one reflected it off of the back of the air gap and kind of took a tour through Neverland in the process, right? So you get two reflected waves, and even though this pink one has 100% amplitude, this orange one undergoes a phase shift, and because of that phase shift is going to interfere with the pink one. So that means the combination of these will undergo partially destructive interference, and the combination will have amplitude less than 100%. Does that make sense? Okay. All we're going to do now is the math for this. And I want to really encourage you all to think of light waves and sound waves as metaphors for what happens quantum mechanically, because it really is an exact comparison in many cases. Waves are waves, and they all kind of work the same way. So let's start with this. And Jack, okay, maybe we won't finish up the gory algebra here. It depends on how much gory algebra you want for this.
It's okay. They have some gory algebra in their homework.
They have some Corey algebra in their homework. Okay. So the notes that you gave me don't even get into all of it. So, um, yeah, you do. I'm into that. And folks, I know I keep promising you the full solutions to that last homework set. My life has been kind of nuts lately, so I'm recording stuff as fast as I can record, but I do have to like give priority to 211. Um, so let's set up the potential as a function of position. So here's our coordinate system. Um, as before, this is going to be the position axis. This is going to be the potential energy axis. And yeah, integration by parts, blurg. It's something that is not, there's a geometric interpretation of integration by parts that's sort of elegant, and they don't really do it much in calculus class for some reason that I've never understood. So we're going to say that that is L. This is U naught, the height of the boundary. And in some sense, this is like going from glass to air and back to glass. So, sorry, you didn't mean to talk about your physics homework, Isa. If you all want a meme about your homework, please go right ahead. Memes are always welcome. So, this is what we expect, right? We expect oscillatory things in region 1, exponential things in region 2, and oscillatory things again in region 3, just like this picture. So, now let's write down the wave functions. So in region 1, I have an incident exponential, and I can expect to have a reflected one as well. In region 2, following up with General Kenobi joke after Matt, I haven't seen the most recent Star Wars movie. Is that from that? I'm a bad nerd, I know. Ah, episode 3. I kind of blocked out the prequels from my mind. Like, don't Jar Jar me. So in region 2, right, this is where you have the exponentials, and we're going to have one of both signs. And then finally in region 3, we're back to exponentials again. I'm going to go to F just so I don't reuse the letter E and confuse everybody.
Hey,
Yep.
Walter, what for you means kappa, and what symbol? Is there anything in the way that you write it that
Oh,
can tell me when it's a wave number and when it's kappa?
yes. So K looks like that, and kappa looks like that. It's loopy,
Okay.
and the thing goes all the way to the top. Is I noticed I had always seen kappa like in the textbook that I learned from in my classes, and I noticed that in the notes that Jack sent me, it's alpha. Um, so, Jack, I'm sorry I didn't adopt your notation here. I adopted the one I learned because if I see alpha, I'll forget what it is. Um, and the other way, Isa, is kappa doesn't come with a I in front of it. So now we've got to apply the boundary conditions. Um, so remember how before we said, all right, in the exponentially decaying region, I have to have exponential decay because now, if it was exponentially growing, it would blow up. Remember that logic we made last time? Does that condition still apply? Can I still cross out? Because remember, we've crossed out ones that are non-physical before. Is there anything I can cross out here? Why do you want to cross out G, Matthew? You're right, but why do you want to cross it out? Exactly. There's nothing further to the right for it to reflect off of. Let me just finish drawing what all of these represent. So C is an exponentially growing thing, but that's fine because we only have a finite region, it doesn't blow up. So this is C. D is an exponentially decaying thing. F is a rightward propagating thing here, but G doesn't exist. So let's get rid of G. And now we conveniently have four unknowns, right? We don't know B, C, D, or F. And we have four boundary conditions. Um, right? What are my four constraints that I have? Um, yes, C is, well, actually, yeah, it is kind of switched. C is the reflected evanescent one because it decays going to the left, and D is the transmitted evanescent one, the one that decays to the right. So yeah, if you want to think about like a direction of travel, um, C is going rightward, and D is going left. Good point, Charles. Yeah, so Matthew is writing grad for derivative. Like, yes, that's how you do it in three dimensions. But the four constraints that I have are that both the wave function and its derivative have got to be continuous across both gaps. So that tells me that psi1 of 0 equals psi2 of 0. Psi1 prime of 0 equals psi2 prime of 0. And then the same thing happens at L. So psi2 of L equals psi3 of L, and psi2 prime of L equals psi3 prime at L. So now all that's left is to apply those things. Now I'm going to skip over some amount of um, like taking derivatives manually. Stop me if there's something that you don't understand, a term that you don't understand where it comes from. But I'm going to skip a few steps here in algebra. So I'm going to call these constraints with um, with Arabic numbers 1, 2, 3, 4. So constraint 1 gives me, pretty simply, a plus b equals c plus d. That one's easy because all of the exponentials go away. Constraint 2 gives me the same with their derivatives, so this is kind of the same thing that I had before. I get IKA minus IKB equals kappa C minus kappa D. Now, the constraints for 3 and 4 are a little bit more complicated because now I can't just throw away the exponentials, right? Um, so for 3 and 4, I get, so constraint 3 is matching the wave functions between 2 and 3 at x equals L, right? And that's what's going to give me the exponentials that are going to be a pain in the butt to deal with. Is I've got to deal with x not being 0 anymore. So matching that on, that's going to give me kappa c e to the lx minus kappa d e to the minus lx, whoops, l kappa, kappa l. So that's the left side. Oh, no, I'm not supposed to take a derivative yet. I'm doing the wrong one. That's constraint 4. Let me back up. So this just gives me ce to the kappa l plus de to the kappa l equals f e to the ikl plus g, well, that one doesn't exist, right? We crossed that one off. And then constraint number 4 is the one that I was about to write down a bit ago. So this is the one where I take the derivatives of 2 and 3. So the derivatives are going to pull down factors of kappa and ik. So this gives me kappa c e to the kappa l plus, there's a minus sign there, so minus kappa d e to the minus kappa l equals ikf e to the ikx. So here I've got a system of 4 equations and 4 unknowns. Does everybody understand where those equations came from? Okay. So, Jack, this is where I will appeal to you, if you're there. Do you think it's worthwhile in class to chug through the algebra for this?
Probably not.
Probably
Um,
not. Okay, so
um, but yeah, I mean, maybe just be aware of how to actually, you know,
how to do it?
how to do it. Just sort of outline it.
Yeah, yeah.
Um,
So this is, my strong point has never been like grinding through algebra, but systems of equations like these can typically be done with substitution. So you solve for one variable, you substitute it in, you find another variable. Um, so what you would, you could just go one at a time. Is that what you had in mind, Jack?
well, yeah. So I mean, this is, you've kind of outlined this how to go about solving this thing,
Mhm.
and then sort of just I would have reiterated how you'd get the transmission and reflection coefficients.
Yes. Yes, that
Um,
is.
in, yeah.
That is, yeah. So we'll do that. So let me just get started with this. So I get b equals c plus d minus a. So then I can plug that in here, and that gets me um, IKA, and then all of this stuff is b minus IKC minus IKD plus IKA equals kappa C minus kappa D. All right, so now we got rid of all of the B's. Now, grind through this and solve for C, and plug it in there and solve for D. And then grind through that one and solve for D, and plug it in there and solve for F. I don't really know a simpler way to do that. You will wind up with a whole lot of exponentials flying around, but um, let's talk a bit about as Jack said, finding the transmission and reflection coefficients. So algebra will happen, and we get values for A, B, C, D, F. Well, B, C, D, F. So algebra happens, and we find B, C, D, and F. These are the reflected. Again, this one's reflected. That one is transmitted. And C and D are both evanescent. Um, so we talked about evanescent waves in optics. In quantum mechanics, this is called tunneling. The idea that a particle, if you throw a particle at a boundary, it can tunnel through that boundary in a region where it's classically not supposed to be, and it has some probability to pop out on the other side. Now, if we're interested in the reflection and transmission coefficients, um, remember before that the reflected coefficient is just going to be the norm of b squared times h bar k over m, And the transmission coefficient will be 1 minus that, which is also the norm of f times h bar k over m. So you can, in principle, solve this. Looking at yeah. So there are some formulas. So Jack, the formulas for this are in their books, right? Because I don't have the textbook.
That's right.
Okay, so I'm not going to grind these out. They're actually, the typesetting is garbled in the notes that I have, and it would take me like way longer than the time that I have left to do all the algebra here.
Yeah, no, it's fine.
This is kind of interesting though. There is, though, one other thing that's worth talking about, which is what happens here. So here we have thought about this case where the energy is less than U naught. Could I do this here where the energy is greater than U naught? What would I have to do? What would be different if E is greater than U naught? Nick says yes. So what do I do? Yeah, so instead of kappas, I have k's. So in this case, this would be analogous to this scenario. Let me draw it out. So here are my coordinate axes. Here my potential looks something like this. Right? But now, if the energy is greater than the height of the barrier, now it's still an oscillating thing in the middle. So now I've got, on the left, I have AE to the IKX plus BE to the minus IKX. But now in the middle, I have an oscillating thing. I have CE to the, it's some other wave number, right? And then on the right, I would again have FE to the IKX again. So what we saw earlier is that whenever a wave reflects off of a potential step, it picks up a phase shift on the way back. Right? So you're going to get multiple reflections in the middle. You know, the algebra will take care of this, but if you want to think about like particles bouncing back and forth, there's some amplitude to bounce off of the left, and then bounce off the right, and then bounce back off the left, and then bounce back off the right. So there's going to be some sort of standing wave inside the step, because that's all a standing wave is a thing that continually reflects back and forth, back and forth, back and forth. So let me now ask one other question. We're going to go back to optics, and this will be the last thing we do today. Imagine this optical system. So let me tell you what these are. So this is air. This is air, or maybe it's glass. And this is a very thin layer. It doesn't really matter what it's a very thin layer of. Yes, Grant, exactly. The standing wave, the energies of the standing wave depend on L. They also depend on K prime. So let's label this here. So boop. So there are standing waves here. Um, they're how should I say this? Their energies depend on K prime and L. Now, what we saw before, so these multiple reflections that produce standing waves, if those reflections give you a complex phase shift, then they'll partially destructively interfere with each other, and the standing wave will not stand. But if we tune it just right, yes, Yanju, that's what K prime is. Um, yeah, K prime here, because here the energy is greater than V, so we always have a real wave number. If we choose the width of the barrier and its height so that the energies match the standing wave energies, the thing you already studied, Grant, then you will get standing waves inside here. So one way to think of what happens in this situation is you've got an incident light ray, I can talk, a transmitted light ray. You have one that's reflected from here, and then you have in the gap standing waves. But if you choose the thickness of that layer of air just right, then the thing that comes out the other side, we argued that there will be a thing that comes out the other side. If you choose that just right, then these two will be 180 degrees out of phase and will cancel completely. So I'm sure some of you wear eyeglasses, right? Take your eyeglasses off if you wear them and look at their surface. In particular, hold them so that you have a bright light behind you and look at the reflection of that bright light in your eyeglasses. I think some people wear contacts, Eva, but look at the reflection of some bright light in your eyeglasses. If you don't have eyeglasses, look at the reflection of some bright light in your computer screen. What do you see? Or your cell phone screen will work better. You'll notice that lights don't reflect very well off of your eyeglasses or your cell phone screen. That's because they're coated in a very thin layer of a material. It doesn't really matter what it is as long as it's thin. That's tuned so that its thickness and the wave number inside of it are the wave number and thickness that would give you standing waves for the wavelengths of visible light. This is called an anti-reflective coating. Um, so that suppresses reflection, and the transmitted ray is nearly 100%. So this is how you make an anti-reflective coating for eyeglasses or for the surface of a cell phone screen. The reason that you see like really dim colors is because different wavelengths of light have different K values, basically, um, or excuse me, different wavelengths. So you need a different thickness of the coating. So a coating that works for one wavelength won't quite work for another wavelength. Um, so this is the end of class. Jack, are you planning on being back on Tuesday?
Yes.
Good.
So my plan actually uh, was we finish up. This is chapter 6, right?
Mm-hmm.
Tunneling and so forth. Uh, Waves approaching a barrier. Um, so I was thinking that we would actually next week skip to chapter 12, which is particle physics. And some of these chapters are clearly pretty sequential, right? You wouldn't want to do this chapter without having done chapter 5, but chapter 12, um, you can do. I can talk about particle physics, a bit more about antimatter and things like neutrinos and all of that. And what are all of these crazy particles and how do we understand them? And that's kind of separate from the other material. And since we only have a week, yeah, Walter, if you want to come to that, be my guest. Um, so this was basically the lecture for chapter 6, and then you'll finish the homework for early next week. And then I've got there. We'll do a few problems. The problems, I mean, there's a number of them, but they're not that difficult. A lot of them are writing down things like Feynman diagrams, which is actually pretty straightforward and kind of fun. We are not going to do chapter 7 um, for two reasons. So particle physics, is that something that would be on the final? Um, if it is, it'll be at a very simple level, and at the level that you've seen in chapter 12, and you also have several days to work on it. So in fact, that would probably be the sort of more fun part of the final, if there's like half a question with something on that. Um, but Yeah, so chapter 7 we didn't cover. What that was basically the hydrogen atom, applying all of these techniques that you've learned, solving the Schrodinger equation for bound states. Instead of an infinite potential well, it would be for a Coulomb potential in 3 dimensions, and you'd find that the properties of the Balmer spectrum and all of the stuff you do in chemistry, this stuff comes out of solving the Schrodinger equation for the hydrogen atom. And the electrons can only take certain discrete energy levels, just like for the infinite potential well or for the harmonic oscillator. So, and the technicalities become more challenging because suddenly you're solving the Schrodinger equation in 3 dimensions in spherical coordinates. And if any of you have ever written down the second derivative, what we call the Laplacian in 3 dimensions, it's pretty ugly. But those of you who will be taking quantum mechanics will get to see all of that stuff. It's just you kind of see it twice. And so what we cover in modern physics and what you get in quantum, there's a lot of overlap. And this year we're not getting to as much. And so since we don't have the time to really get into chapter 7, given all the machinery that we'd have to introduce, we might as well do chapter 12 and have some fun doing particle physics. I mean, it's supposed to be fun. And that's actually my